This is Austin Lando.
And Nolan Snellgrove.
Our heat transfer project analyzed the effects of surface finish on heat transfer for forced and free convection. I took an interest in conducting a project on surface finishes because I was curious whether a smooth or rough surface was better for rejecting heat in a handful of automotive circumstances. For example, many air-cooled Porsche engines came stock with cast aluminum cylinder liners. The cast aluminum has an inherent rough texture. In the high-performance aftermarket, there are many offerings for billet aluminum replacement cylinder liners that promise better cooling and all-around high performance. I was curious if the smooth surface finish made a measurable difference in the convective heat transfer from these cylinders and could improve performance in any way. Additionally, I was curious if surface finish could affect heat transfer from a simple tubular heat exchanger, such as the power steering fluid cooler pictured on the right that came stock on early 1990s Honda Accords. The objective of our project is to determine how surface finish affects convective heat transfer rates. We will conduct our experiments using aluminum cylinders. In this slide is shown some useful theory procured from the textbook. First, it is important to recognize conceptually that laminar flow of forced convection over smooth cylinders corresponds to a smaller angle of boundary layer separation. According to the textbook, a separation angle of 80 degrees corresponds to laminar flow in heat transfer applications. A separation angle of 120 to 140 degrees corresponds to turbulent flow. Characteristic of turbulent flow is increased mixing and elevated levels of heat transfer. Secondly, it is important to note that there are no known average Nusselt correlations available for smooth cylinders under forced cross-flow convection at Reynolds numbers above 200,000. The textbook offers a chart of local Nusselt correlations for a small handful of Reynolds numbers as shown in the lower picture, but these correlations are of little use to us.
Previous research experiments conducted by Eichenbach developed a Nusselt correlation for flow over knurled cylinders in the context of how the texture of ice frozen on wires affects heat transfer. The aluminum cylinders used in this experiment fall under the lump capacitance model with Biot numbers less than 0.1.
With the knowledge that turbulent flow corresponds to increased heat transfer rates from smooth cylinders and flat plates, we hypothesized that, under forced convection, a rough textured surface over a cylinder would cause the boundary layer to trip and force turbulent flow to begin shortly beyond the stagnation point. This turbulent flow would contribute to increased heat transfer and faster cooling compared to a smooth cylinder of the same dimensions.
This experiment was an extension of the forced convection lab, and some of the data was carried over for use in this experiment. Specifically, the data gathered for forced convection over smooth cylinders was taken from that lab. To gather data for rough cylinders, new rough cylinders had to be constructed. Cylinders of aluminum were turned on the lathe to 12 and 17 millimeter diameters, and a knurling tool was used to add a surface finish as seen in the image to the right. The cylinders were heated and placed in the wind tunnel. A thermocouple was placed in a hole drilled in the metal to measure centerline temperatures during cooling. Air was blown over the cylinders at speeds ranging from 4.3 to 47.8 meters a second. The cooling timers recorded the cylinders cooled from 40 to 28 degrees C.
Following the wind tunnel tests, the knurled and smooth cylinders were placed in the water table to compare angles of boundary layer separation. Congruent with the values given in the textbook, the smooth cylinder displayed a shallower angle of about 75 degrees. This is shown on the right. The knurled cylinder displayed a separation angle of approximately 120 degrees. From these experiments, we concluded that the knurled cylinder indeed tripped the boundary layer and forced turbulent flow.
The emissivity of polished aluminum is approximately 0.05. A thermal imaging camera was used to estimate the effect of the knurling on emissivity. The emissivity was estimated increased to 0.53 after knurling was done. However, radiation accounted for only 0.1 to 1% of total heat transfer and was neglected from further calculations. There was a significant drop in cooling time from smooth to knurled cylinders for both large and small sizes as seen in the above figure. The average time drop for the small cylinder test was 7.1 seconds, and the average time drop for the large cylinder test was 16.6 seconds.
Using the lump capacitance model, heat transfer coefficients were determined for the smooth and knurled cylinders. From those heat transfer coefficients, Nusselt numbers and correlations were calculated. This plot shows how the Nusselt number varies with Reynolds number for both the smooth and knurled cylinders. Interestingly, at this point, there is little difference between the Nusselt correlation for knurled and smooth cylinders, at least in this relatively narrow range of Reynolds numbers. This indicates that the heat transfer coefficient is not drastically different for the knurled cylinders. This is contrary to our hypothesis. We noted that, by the lump capacitance model, the only variables that are different between the knurled and smooth cylinders are heat transfer coefficient and surface area, both of which cooling time is inversely proportional to. So, if the heat transfer coefficient has not changed much, the surface area must have increased markedly to yield such a significant reduction in cooling time. To determine how significant the difference in surface area truly was between the knurled and smooth cylinders, all 4 cylinders were modeled in SOLIDWORKS. The dimensions of the knurling patterns were carefully measured and applied to the smooth cylinder models in SOLIDWORKS. The surface areas of each cylinder were measured within SOLIDWORKS and compared against the values for the smooth cylinders. The results were staggering. The small knurled cylinder yielded about 15% more surface area than the smooth cylinder, and the large knurled cylinder yielded about 20% more surface area than the large smooth cylinder. Such large increases in surface area should very likely contribute to decreased cooling time. After calculating new surface areas for the knurled cylinders, a new Nusselt correlation was generated for the knurled cylinders. The new curve fit correlation was found to be surprisingly close to the Nusselt correlation for rough cylinders by Eichenbach. From this information, we conclude that the increased heat transfer rate and decreased cooling time is due more to the increase in surface area from the knurling process than to the delayed boundary layer separation.
The smooth and knurled cylinders were again heated and allowed to cool from 40 to 28 C, but under free convection conditions. The results were inconclusive and there is no noticeable difference in the cooling times between smooth and knurled cylinders during free convection.
So, to sum up, we learned the following from our heat transfer project. Roughening a surface does in fact increase heat transfer under forced convection. The increase in surface area due to knurling likely contributed more to the increase in heat transfer than did the delayed boundary layer separation caused by knurling. Radiation effects were considerably small and can be disregarded for the purposes of this experiment, and our data doesn't show any significant gain in free convection heat transfer by texturing a surface.